All right, hello. This is our first lesson for the matrix unit. We'll talk more about what matrices are, what they're used for, and what our goals are for this unit. We'll talk about that coming next week. For today, this is an excellent intro to what we'll be doing within matrices, and that's solving systems. Now, typically with solving systems, you have a situation where you have like an x plus y equals 7, and then like a 2x minus y equals 10, and you go, oh, I'm going to add those together, cancel out the y's, and solve for the x's. Well, those are the types of systems when you have two variables, and now we're going to be looking at systems with three variables. And let's follow the pattern here in terms of the relationship between number of variables and equations necessary in order to solve. So if I have like one variable x or y or whatever, if I have it in one equation like 2x plus 4 equals 8, I can solve. So if we have one variable, we need one equation to find that find the value of the variable. If we have two variables, we need two equations, just like we just saw. Therefore, if we have three variables, we need three equations. And we could continue that on. 4 variables, 4 equations. How do we solve that when we have 4 or more variables? That's when we get into matrices. But for today, we're just looking algebraically. What are the methods that we use to solve 3 variable equations? Now, this is going to be similar techniques to what you saw within solving systems of 2 variables, like elimination, or what is also called linear combination. But we are going to structure it somewhat differently because that's going to lead us into how to solve with matrices, which is going to be the main objective of this unit. Okay, so let's look at number 1. Our goal, if we have x, y, and z, we have 3 equations. And if we look here, this is a great setup for what we need to get to in order to solve. So if you look here on the third equation, we have z equals 2. Well, if I know that z equals 2, I can then substitute in for here, and then I could get the value of y. And now that I have y and z, I can substitute that in to the y and z up here and solve for x, and then I have the values of x, y, and z. So this is the idea of what is called back substitution. This is the structure that we are looking for, where if we have, generally speaking, if we have 3 variables equal to a number, 2 variables equal to a number, and then 1 variable equal a number, we then can solve and find the values of x, y, and z. So let's first go ahead and do that. We have z equals 2. We substitute that in. So now I have y plus 3 times 2 equals 5. And that'd be y plus 6 equals 5. And then we have y equal to negative 1. And now we're going to take the y value and the z value and insert them into the top equation. So I have x, and that would be negative 2 times negative 1 is positive 2 plus 6 is 8. So I have x plus 8 equals 9. And then subtract over the 8, x equals 1. I don't think I made any small silly errors. So what does that mean? Well, if you look here, z equals 2, that's kind of like x equals 2 or y equals 2. Graphically would be lines, but since we're talking in 3 dimensions, these are going to be planes. You can think about planes like the ceiling, the wall, the floor, the desk. Those are planes in 3 dimensions, and those planes are going to intersect. So if you look at 2 walls in the room, 2 adjacent walls, and the ceiling, they all intercept at a point in the corner of the room. What is that coordinate? Well, that coordinate needs an x, y, and z, and that's exactly what's happening here. So I have an x value of 1, a y value of negative 1, and then a z value of 2. And so these 3 planes, whatever they look like geometrically, which we don't even have to understand completely, even though I gave a kind of a very crude diagram right here. It shows like 3 planes intersecting somewhere in here at those points, at that one point. This is an example of when 3 planes intersect at one point. All right. So what happens now? To recap, if we get to this situation where we get one variable, preferably z, as we'll see later, y. In the third equation, 2 variables and 3 variables, we can do what's called back substitution and find all the values. Okay, so now what happens if I have this situation where I don't have one variable in the last equation. What can we do to solve? So there's going to be a relative straight procedure that we are going, or a guideline that we're going to work on, even though at times that procedure may seem non-intuitive. So the procedure that we're going to do, and this will be a lot more clear when we get to matrices, is in these last two equations, if I can get a y and a z in this equation only with no x's, then we are in a situation where we have two variables with two equations, and then we go to our solving systems method, just like I showed at the beginning. So that's what we're going to do. The first thing we're going to do here is aim to eliminate the x in what I'm going to call row 2 and row 3. You don't have to write that. This is just kind of written notes that I'm doing as I speak this out. So what is row 1, row 2, row 3? Well, it's actually quite simple. We're going to call the first equation row 1, second equation row 2, and the third equation row 3. And given the fact that this can get a little more complex, and this also sets us up for when we're solving for matrices, we're going to show what our operations are in order to eliminate the x. So what I'm going to do is use row 1. Typically we're going to do it in this fashion. Nuances we'll work on later. Row 1 we are going to use to eliminate the x in row 2 and the x in row 3. So let's first work on row 2. If you look at this x and this x, you see that they're opposites of each other. So just like we did within solving systems, you add or subtract when the coefficients are the same or opposite. Now your teacher may have taught you, always get them opposite. That's a preference. I prefer to just look at what you have, and if you have them the same or opposite, then you decide. If they're the same, we subtract the equations. If they're opposites, we add. That's my preference for two variable systems. For the methods that we're going to use here, our goal is to always add the two equations. Like I said, that other teachers prefer with two variable system. For three variable systems, like I said, it's preferable for us to always add. So what I'm going to do is I'm going to look at this and go, okay, I have x and negative x, so I just need to add those two, which I'm going to do. So, but I'm going to write it over here to indicate that I have row 1 plus row 2. And when I add those together, that's going to give us a new equation that we're going to insert into row 2. Now, there's a reasonable amount of writing here. So I think it would also be preferable for us to try to eliminate the x in row 3 at the same time. And then when we write out our next version of this system, we aren't doing more work than necessary by having to rewrite it a third time when we could do it all in one step. So now, that being said, I want to eliminate the x in row 3. So when I eliminate the x in row 3, I have a 1x here and a 2x. And remember, I do want to add them. Okay, so I want to add them. And again, I can't give reasonings yet for why we're wanting to always add, but it will hopefully be more clear as we go through the unit. So I want to add these. For row 1, I need to multiply this by negative 2 in order to add it with that. So over here, I'm going to write negative 2 times R1, and that, whoops, and I need to correct this. This is not supposed to be row 2. This is supposed to be row 3. Row 3. And now that I'm going to take negative 2 and multiply by row 1 and add it to row 3, we are going to take that new equation and replace row 3 with that. We could replace it with row 1, but that's not what we want to do. We want to replace row 3. Note, since these are a little more complicated, even though we're doing the exact same mathematics as solving with 2 variables, we're just doing it with 3 variables, it's nice to write this, as it also is kind of like a bookkeeping organization for, we can make small errors, fallible as we are, and therefore we can look back at those operations over here that we're doing in order to get what we get to recheck our work. So now after we figure out our row operations, I'm going to rewrite row 1. We did nothing with it, so I'm just rewriting it. Anytime I write my z's, I put a line in it, so 2, indicate that it's not a 2. Now remember, with row 1 and row 2, right here, we're adding them to get the new row 2. So if I add these, I'm going to add the x's, those go to 0. I add the y's, negative 2y plus 3y gives us 1y. And then I'm going to add the z's, 3z, and there is 0, 3z plus 0. I just go ahead and add those. 3z plus 0 is 3z. And that is equal to 9 plus negative 4. The constants, 9 plus negative 4, is going to equal 5. And so now I have a row 2 with a y and a z. Now we're going for elimination of the x in row 3. We're going to take negative 2 times this, negative 2x plus 2x is 0. Now keep in mind, I actually mentally go through that calculation just to be sure that I did my row operations correctly on the x terms. For the y terms, I have to do negative. Remember, we're multiplying everything in this equation by negative 2. So negative 2 times this would be positive 4 plus negative 5. So negative 4, or positive 4 plus negative 5 is negative y. Again, negative 2 times negative 2 is positive 4 plus negative 5 is negative y. Now we go to the z terms. Negative 2 times 3 is negative 6. Negative 6 plus 5 is negative z, so I have a negative z here, equals. Now I do the constants. Negative 2 times that is negative 18, plus 17 is negative 1. And now I have a 2-variable system with the y's and the z's. Our goal is to, in this case, it's going to be easier to solve for z. But even if it's a case where it's not easier to solve for z, please still solve for z, which we'll see in a further problem. So if we look here, we want to eliminate the y's, and that is among the row 2 and row 3. Notice at this point we're going to leave row 1 alone because we got that xyz like what we want. So we're going to add these together. We're going to take r2, so I've been doing this in red, r2 plus r3, and that is going to eliminate the y, so we just have a z, and we want that to be in row 3. So now we write our next version of the system. Nothing happened to, sorry about the sloppiness. Writing on with the stylus on the iPad doesn't always work best for me. I did nothing with row 1 and row 2. I used row 2, but I'm adding it to row 3, but that eliminating row 3. So now let's look at our operations. Row 2 plus row 3. So I add those go to 0. I add these. I have 3z minus z is 2z. And then 5 plus negative 1 is 4. And if you look right here, we already can easily solve for z. I don't expect you to write out a whole new line with just z equal to 2. You can just go ahead and cross those out and go z equals to 2. And now you look, we are in the exact same situation as we are up here. In fact, it's the exact same problem as right here. So once we get to here, now you go ahead and back substitute, which we did up there. So in your problems that you have in the homework, you're going to eliminate like this as best as possible, solve for z, and then back substitute. Okay, let's take a look at this one. So now we have some interesting things happening. If you look back at that first problem, it really helps in this upper corner here if you have a 1 for the x. Okay, so if for the coefficient right here. So what we're going to do is what is called row swapping. And since I'm doing this lesson on video, I'm only going to do one step at a time. It is possible for you to do more steps at a time, but I'm only going to do one. So I could row swap with row 1 and row 2 because I have a 1x, or I could do row 1 and row 3. I think row 3 is a little nicer because I have x, y, and negative z. That's a little nicer than 1, negative 2, negative 3 as coefficients. So I am going to, the first step I'm only going to do to get that x, 1x in the top corner is what is called row swapping. Row 1, and those are two arrows going back and forth, swap with row 3, x plus y minus z equals -1, x minus 2y minus 3z equals 2, and then 2x plus 4y plus z equals 1. Now, if you look at the completed notes I have posted here, I believe I solved this differently because I typically, if I solve this one in person, I try to do more steps at once. Potentially, I haven't looked at the completed notes before I started this lesson. So now let's just go ahead and go through the same procedures we did before. We have these are the same, so we want them to be opposites of each other, meaning I'm going to take the opposite of row 1 and add it to row 2. Once again, we always want to add to that row 2. So that's why I put the negative in front of the x, or in front of row 1. And the same thing here, I have a 1 and I need to get a 2, so I need to multiply this by -2 to eliminate. So I'm going to go -2 times all over row 1 plus, and this is added to row 3, and that's going to give us a new row 3. So first off, I'm going to rewrite the first equation. So now I'm going to combine the first equation with the second, or row 1 with row 2, by doing the operations over here. So the opposites of all of these plus those, so -x plus x goes to 0. -2y plus -2y gives us -4y. Then we have opposite of z, opposite of -z, so it's z plus -3 would be -2z equals, and then -1, opposite of this would be +1 plus +2 is 3. Now for the third equation, or third row, I'm going to multiply -2 times the row 1, so -2x plus 2x is 0. -2y plus 4 is 2y. Then we have -2 times this would be +2 plus z is 3z, and then -2 times this, so it'd be 2 plus 1 is 3. Okay, now that we have the two equations with two variables, y and z, let's go ahead and do like we did last time and eliminate the y in the second equation. So we have just z in this equation. So if I look at this, I'm going to have to multiply the second one by 2, and then I'm going to add these two together, because then that would make that a +4. So I'm going to go R2 plus 2R3. That gives us a new R3. Rewrite the first equation. Rewrite the second equation. And let's go ahead and do the operation now. This plus 2 times that, and again I just mentally do the calculation of the one that is going to get eliminated just to be sure. -2 plus 3 is 6, or let's see, -2 plus 6 is 4z equals, on the constants, 3 plus 2 times this is 6. And then if we divide by 4, we get z equals, again, we don't have to rewrite everything. We could just write exactly what it equals, 3 over 2, or 1.5, and then you go ahead and back substitute all the same. Okay, on this one, this is when we will get to the reasons why we use z. We always solve for z in the last equation. It just works out structurally the best in pretty much all cases, especially when we get solutions like we do here. Okay, so We see that we have in the second equation, we have the x eliminated, or the x isn't there, which is nice. So let's keep that the way it is. You may have the inkling to move the z over here, and now we have y. We can do that, but the thing is you're not always going to be able to do that, and we need to practice how to solve for z in that last equation. So really all we need to do here is work on eliminating the x in the third equation, since it's eliminating the first and that would and the second. So we just take R1 and R3 and add them together, which again just simply means equation 1 and equation 3 adding together and replacing that combined equation into row 3. That would give us, just rewriting the first one, rewriting the second. Nice to put them nice and nice and neatly in order. So now I'm going to add row 1 and row 3. Gives us 0. Add those together gives us 3y. Negative 3z plus 0 will give us negative 3z. Equals, add the constants gives us 0. Now if we want it, you may see a pattern there with the y's and z's. It's okay if you don't. Let's go and see. We want to eliminate this y, so I multiply this by negative 3 and add. So now I do the calculations. Negative 3 times that gives us 0. Negative 3 times that will give us positive 3z plus that is 0. So we get 0 equal to 0. What does that mean? Well, if you think back to two variable solutions, if we get 0 equals 0, that means we have infinite solutions. That means that the two lines are on top of each other. But in 3 dimensions, you could imagine that if we have infinite solutions to planes, look up in the corner of the room. If you have the ceiling, which is a plane, meeting with the wall, which is a plane, they meet at the corner, or the line, the intersection of those two planes is a line, the corner of the whole room. Not the corner, but the top line. And therefore, our solutions, when we have infinite solutions, could be a line. And therefore, we want to somehow mathematically represent that line. The way we're going to do that is set z equal to some other variable. The variable that they use in the book is a. Let's just see what happens. Now we think of z equals a, very similar to the problems we had before where z equaled 3 or 5, and we back substitute and then solve for the others in terms of a. So I'm going to plug a into z in the second equation, and then add over, we get y equals a, and now we have x plus in the top equation, y equals a, z equals a, negative 1. And now I simplify over here. A minus 3a is 2a equals negative 1. And now I'm going to add over the 2a. We get 2a minus 1. And so if we write it as a coordinate, just like we wrote the numerical coordinates, x is 2a minus 1, y is a, and z is a. And now if you think of, if we pick a value for a, like 1, 2, 3, and so on, we are going to get points, an x, y, z point. For instance, if I pick 2 for a, I get 3, 2, 2. Well, that point is on that line of intersection. If I pick another value for a, that would give us another point on that line. Now, not all infinite solutions will be lines, but those type details and the different type intersections that we could have for planes is noted here. The type of solution that we just had was like this, where the three planes are intersecting at a line. You can have that specific case where it intersects at one point. All three planes could be the same plane, and then we could have no solutions where they cross kind of like in a triangle fashion, where all three planes do not intersect in one line, or a point, or overlap all three of them in one spot or one line. And then the last one where they're all parallel to each other. Okay, do the best on your homework. Hope you have a wonderful weekend. I'll see you back on Tuesday.